All right. Hello, hello. It is time to get back to the advent of code 2022, day 15, in which we're being asked to prove a negative, sort of. So, last time read through this, thought a little bit about it, but getting back to it today. So, in part 2, our handheld device indicates that the distress signal is coming by a beacon nearby. It can be between 0, 0, and 4 million, 4 million. We have to identify its tuning frequency, which can be found by multiplying its x coordinate by 4 million and then adding its y coordinate. In the example above, the search space is smaller. So this gives a sort of a test case. What is its tuning frequency? And so the thought last time was basically like, look, searching through all 4 million by 4 million, 4 times 10 to the 6th, so 1.6 times 10 to the 13th, is going to be a lot of searching. And so we'd like to avoid doing that. And now, obviously, we won't actually search every single case because we'll find the answer at some point. We know that there's a unique possible position for the distress beacon. So, maybe naively we would expect to search half that space. That's still, something times 10 to the 12. Big number. That said, there's not a huge amount we can do about that because we're being asked to prove a negative, kind of, in a way, right? We can't... Any algorithm we pick has to, at least in principle, be able to visit every single one of the options. And so we can't eliminate that. In principle, the algorithm has to be able to touch every element. Now, there should be ways for us to prioritize to search that space more efficiently. And the kind of straightforward one, and the one that I think we'll start with, is just to search or to eliminate options based on the beacons that have the most the biggest radius. So the beacons, if you remember from the first section, are like this. Sorry, the sensors, not the beacons. The sensors are like this. They create this thing that looks like a diamond. It's a circle with respect to the Manhattan distance. If you want all the points less than or equal to, I guess it's a disk with respect to the Manhattan distance. All the points less than or equal to the distance from our sensor to our beacon, but not using the usual Euclidean distance. It uses the Manhattan or the L1 norm. And so the bigger this distance is between the sensor and the beacon, the bigger this radius is getting, like the bigger the radius of this is, which means the bigger the diamond is. And that means it's going to eliminate more spots. So on average, when we're detecting whether a spot needs to be eliminated, it will be more likely to hit it. This is definitely true, but it's kind of naive in the sense that, like, if the sensors and beacons were set up deliberately, you could pretty easily make this not very efficient, right? You could make all of the bottom right. You make the answer somewhere in the bottom right hand corner, for searching from the top left down. And you could put all of the big radius ones down in the bottom right-hand corner. Also, there's kind of a funny, interesting question of whether we should, it's going to tend to be easiest to search from the top left to the bottom right. There's a funny question about whether we should search differently than that, given that the problem is composed. It also occurs to me that we know the bound, right? We know the that is between 0 and 4 million. And I'm thinking about whether that means that we actually don't want to start by the edges. No, we probably still do. We probably still do. So let's see how this goes. It's not clear to me whether this is going to be fast enough or not. But I'm a big fan of not over optimizing, not optimizing if we don't need to. Like the calculation we're doing every time here should be pretty fast. So, you know, we can implement it, and then, I mean, if it runs in 5 minutes, I don't really consider that a solution to the problem. Like, I think it should run in a few seconds. I can't remember if I think Euler Project gives guidelines on how long the problems are meant to take to solve. It's like a minute or something. I don't remember if Advent of Code does, but I kind of think a minute is about as long as I want to take to solve a problem. Maybe the last few problems. I don't know. I've never had a chance to do all this before, so I don't know how hard or computationally intense they get by the end. So anyhow, let's get into that. So first off, let's set up our sample answer. Whoops. And it's going to be, so it's no longer the 10th row. This is going to instead correspond to the bounds. And so the bounds are 20. So 20 to 2020. And the answer is 56,000,011. And same example input, same input. Okay. And let's go up to the top here. And this is going to be max. What to say? We can just call it search space size. And okay, and so how is this going to be different than the previous solution? Well, last time we had to work out what the min and the max were ourselves, so we don't have to do that anymore. And then, but we are going to want to order these sensors in a compelling way first. Which maybe we just do in from strings, I think. And then the other thing is we don't want to, like, in this case, we exhausted the space. We really don't want to do that this time. We want to, not lazily, what's the opposite? Greedily return, right? So as soon as we see a reasonable place for the beacon to be, we want to return and say that it's that. And then we'll also have to do the tuning frequency part of the calculation. So let's jump into from strings, and we want to sort this. So let's say let mute to return be this, and then we want to sort on a particular thing to return sorts. I. And here we need to know what the comparator function is. And so the comparator function is going to be, what kind of function does this need to be? It takes two arguments, A and B. And it says, actually, we can just say max beacon distance dot cmp b dot max distance. And we want to sort descending. Because we want to hit those first. Okay. So if max distance is, that's right. Okay, so that's one thing. Let's just copy this whole function down, and so this no longer has to happen. We can say let max min x. Oh, but it's not min x and y anymore. So let's just go from, I guess we want to do this in a loop now. Because we want to be able to exit immediately. So let's say for I in 0 search space size inclusive, so +1. Do this right. For j in 0 search space size, and we want to say match this, basically. So let's say let hit be sensors.iter. The sensors are already sorted because they get sorted in from string. Any, so new ij. So the point is, if any of the but that's not quite right. It's all beacon is possible. So this will exit every time that it finds a single failure, which will happen as soon as possible, or at least sooner rather than later, because we're using the widest sensors first. And now beacon is possible. What's the issue here? What's the issue? Expected I32 found U size. Oh, because I and J are U size. Can I just say as as I32? Okay. So that should be fast. And then we just say If hit, then we need to calculate the frequency, which is 400. Is it always 400? Yeah, it is. So 4 million times I plus J. And we return this. And otherwise we keep rolling, and this is not a U size. Can we make it a U size? So we know that this is always going to be positive. So yeah, we can. Actually, I'll love this now that I'm thinking about it. So let's not do this here. And then we'll just do it here as I32, as I32. Okay, and this should never return, and if it gets here, we panic. That's fine. Okay. I think in principle this should work. We no longer need this. And here we go. Solve problem 15b. 4 million. Yeah. Okay. So our query is failing. Which I wouldn't expect. Sensors. So this, somehow we changed our answer. Oh, we changed our answer just because we're no longer, we sorted these. That's slightly annoying. Let sensor IDX be sensors dot binary search. Vec2 new 87. What's the issue? Fair. I guess I can just inspect it is the easiest thing. This is parochial. It's specific to the fact that I, what's going on here? Oh, am I not compiling for some reason? Should be. Cargo test. I didn't want to do that. Cargo test. Problem 15. Okay, and I want to debug this. Okay. Not sure what the issue was there. Okay, sensors 87 is position 1. So all these 6s just need to become 1s. Oops. Okay. Cool. Passes. And okay, so now back to cargo test. And this is failing. Okay, so this is failing on our example input. Looks like it's finding something at 2,10. And it's taking a moment to run, potentially, which is slightly concerning. So let's see what's going on. Search space, search space. Is it 2 or is it 20,10? It's 2. So we're looking for the first time that a beacon is possible for all sensors. That looks right to me. We feel pretty confident about beacon is possible. INJ is my definition for the frequency correct. Multiply its x coordinate by 4 million and then add its y coordinate. Yeah. So I guess another way to do this that I'm not going to do until I get this debugged and see that it's slow, but another way to do it might be to populate a set with all of the elements and then do set differences, which is essentially going to work out to doing hash maps. It's possible. That's faster. I don't really think it is, though. Okay, so why does it think that at 2,1 there is a success? Is this an issue where at 2,1 there's a beacon? I bet that's what it is. Is there a beacon at 2,1? There's at 20,1. 2,0. Oh, 2,10 is where it's getting at. There's 10, 20, and there's 21. And there's 20. But the beacons. Yeah, 2,10. There's a beacon. Okay. So we need to also beacon is possible, and there's no known beacon has to be the thing. And sensor.beacon position doesn't equal. And also, we shouldn't be instantiating this over and over again. Whoa. What happened there? Let position be this, and then position. Did I screw up my parentheses? No, that's okay. and then it's not equal to position. A bit slow. Seems like it got past the test case. Okay. Let's think. So if we did this in terms of hash sets, we would instantiate a gigantic hash set. Might not fit in memory. We would instantiate other smaller, but also possibly big hash sets. We would take differences. The differences would be pretty efficient. But the problem is the instantiation would be slow. Interesting. So, okay, yeah, that's more than a minute. And I assume that if I comment this out for a second, that this test runs. Yeah, and it runs basically instantaneously. Okay. So we've implemented it correctly, it's just not optimized. All right, let's check. So just to think about this for a moment, we're being asked something like find xy such that for all sensors in the sensor, some set of sensors, xy is greater than the radius of that sensor. Which is the same thing as xy such that for all s in s xy, let's see here, not xy is less than or equal to r of s, which is the same thing as for some there exists no s in s such that this is true. By De Morgan's laws. Just no s in s such that x y is less than or equal to. Yeah. Just trying to like intuition pump my brain for other approaches. and it's unique. We know that the XY, we know that the solution's unique, so we only have to find it once. So possible sources of optimization. Uniqueness. Hit the answer as early as possible. Deduplication. Don't perform the same operation multiple times. Anything else? Test monkey pool optimizes times. Not really thinking of too many others here. So we've already tried check the most likely sensors first. We're already doing. Maybe some kind of divide and conquer. Like, one thing that's true is for a given candidate, like, we certainly don't have to check. Right now we're checking every sensor. Question, do we need to check every sensor every time? Well, no. But it's hard to imagine checking, like, basically the optimization. If we tried to do an optimization like, oh, let's look at them in order of how far they are away, it doesn't work, because to compute and sort by how far they are away is going to be more expensive than just checking them all. There are only 19 of them. Or 20 of them or something. Can we trade space savings for time savings? So one idea would be use hash sets, but instantiating 4 times 10 to the 6 squared hash sets seems bad. Maybe it's not. We're populating it with what? We're going to be putting just a vec2 in there. So it's 2 I32s. So it's 64 bits. So it's 64. So it's like 100 bits, which is 10 to the 2. This is like 10 to the 13, so it's 10 to the 15. Nah, that's enormous. That's really, really big. Can't do that. Is way too much. Is way too test monkey pool. Is way too much. Autocomplete. Always nice. So, if I was doing this on pen and paper, it would take me infinity time, but, well, no, I would die before I was done with it, though, or something, probably. But what would I do for a simple case? I would draw the circles. So, okay, so one thought is that these are, like, it's disks. So every time the options you're eliminating are disks. But in order to encode that, you really only need to know the circle. There a way to, like, there are only 19 sensors. So, like, even though it's over this huge space, 19 sensors, I don't know how many there are. There are not very many. There are, 19. So, like, it's a fairly simple condition. So what I'd like to do is basically some version of the uniqueness check. Like, don't check every pair. Here's an idea. We know that it's unique. Okay, this should work. Here's an idea. We know that it's unique. And so it has to either be, it has to be on the boundary of at least one circle. It has to be like one outside of the boundary of at least one circle. And if it has to be on the boundary of at least one circle, all we have to do is check those boundaries. That should do it. I wonder if that's the usual solution here. If it does feel like there's opportunity here, but let's do that. So rather than looping through absolutely everything, we will instead get our sensors. We'll say for S in sensors.iter XS for let's say position in s.getBoundary what do I want to call it? It's not really the boundary. It's one outside of the boundary. I don't know. Naming things is harder. It's hard. Outer layer, corona, surface. Let's call it surface. It's descriptive enough, at least, that it'll make me think about what it is if I ever try to use it again. And then we don't need this, and the rest of this should work. So the idea now is to go through all the sensors, grab all the points that are just outside of them, and work out whether the beacon's possible there in the same way we would have before. Because the point is unique, it's guaranteed to be on the surface of one of these sensors, which feels a little like cheating, but because certainly you wouldn't know this in the real world, but it's all right. And I mean, the proof is, suppose it's not on the boundary on the surface, then there are no sensors within one of it, but that means that moving one over, you get another answer, violating uniqueness. Okay. Cool. So let's just implement get surface. Function get surface, and it will return a vector, I guess. Really should be a hash set of vector2. And what to say here? So we want to go max beacon distance +1 in across and up, and then we want to go diagonally to the others. It's probably the easiest way to generate this. So so we can say let bottom be self dot position plus self dot position, no, self dot max beacon distance times vec2 of j. Top is self dot position plus minus self max beacon distance times vec2 of j, and then these are the same except that it's left and right, and this is plus minus is fine. Wrong order, I guess. Let's go let top left quadrant be vec2, get points between, left and right is fine. No, not left and right. Top left is left to top. We'll say let top right quadrant be the same thing, but top and right. And then bottom. Bottom right. Wait, this should be bottom left. And bottom right. And these will be bottom, bottom, and left, right. Okay. And then we just need to union all of these together. So we can say, I think we can just say top left quadrant dot union. Oh, why are these vex? So something like that. Import hash set and union top right should be why aren't we happy here? Because we get a union at the end, which isn't what we wanted. Can I keep unioning here? Sort of doubt it. Collect. And why not? Okay, because when we union, we only get references back. And we'll just do this. Let's see here. Bottom left and bottom right. Okay. I think it's probably worth writing a test for this. Also, multiply is not implemented for VAC. Feels like it is. I think it's just implemented for I32s. Is it? I thought somewhere. JK, addition and subtraction is, but okay, multiplication isn't. Fine. Let's just implement that. Impl mul for vec2. We want it to be mul I32 for vec2. Type output is self. And mul, will it fill this in for me? Hey, it does, that's nice. Self x is RHS times self x, and y is RHS times self y. Okay. just need to cast these. So let's say let beacon distance. Also, we want this to be +1. So let r equal self dot max beacon distance +1 as 32. And then all of these become didn't quite do it. Searching everywhere. There we go. Max beacon distance becomes R. What's the problem? Didn't we just having BIM issues? There we go. Max beacon distance. There we go. R. And doesn't like multiplication because it's not on the right hand side. Molvec2 is not implemented for fine. Let's just do it this way. And we're still not quite compiling. Why not? Because I times j no longer exists. It's position.x and position.y. And we can do this whole thing. Take this whole thing and try into, which it certainly should. Okay. Oh, we should probably test the, yeah, it failed, but it failed super fast, so that's good. Right. Okay. So I guess we need to update. So the problem is that our vector get points between is failing because they're not horizontal lines, they are diagonal lines. So we would like to include diagonal lines in here, in which case we would need what? We would need left dot x minus right dot x to equal the absolute value to equal left dot y minus right dot y dot absolute value. Okay. So now it's not going to assert, but it's also not quite going to work. Well, maybe it is going to work, because the signum is going to be like 1, 1, or 1, 0, or like negative 1, 1, and so on, right? This should work, I think. Let's add a test. Let's say assert equal get points between 1, 2, and 3, 4. It's going to be 1, 2, 2, 3, 3, 4. And we can do one other one that tests a weird direction, like 1, 2, negative 1, 4. Does that work? That means we're going left and up diagonally. That should work. So this is 1, 4, 0, 3, and negative 1, 4. Cool. That worked. Very nice. So we are compiling. Might have done this right. Problem 15 fails. Why did it fail? Tried to unwrap something that wasn't an int. So it's hitting some result. But what? It's negative? That doesn't seem... oh, that is possible. That is possible. So we should say into iter dot filter 0 is less than or equal to, let's just do it this way. Let's do it in a separate line, I guess. Let surface be this, filter be, and then this will be surface. And in here, oh, and we'll need to collect. And I guess it's going to need to know what to collect it into. Actually, maybe don't have to collect. It can just be an iterator. And the filter will be that 0 is less than or equal to v.x. and 0 is less than or, and let's say search space size is greater than, or v dot x is less than or equal to search space size, and 0 is less than v dot y, and v dot y is less than or equal to search space size. And this can be dot into there. And what we can't compare I32 to a search space size as I32. Okay. And how do we do? 15A still passes. That's always good. We haven't broken previous problems. Still not as fast as one might think. I'm surprised, because for 19 points, this should be... I guess I don't know the radius of these points. I guess some of these points are really, really big. But still, we've reduced the search space by, like, an entire... an entire dimension here, essentially. Instead of going 4 million by 4 million, we're going, you know, whatever the radius is. So it's probably like maybe 4 million. Still taking more than 60 seconds though. Okay. Well, we can continue to make this faster. One way would be to do this filter up front. Certainly would speed things up. Oh, okay. So it took a little over a minute and then failed. And failed because it attempted to multiply with overflow. Really? So it got an answer, but then the answer was too big for a U size. Okay. Well, let's return a U64. And we'll say U64. And this will be as U64. And seems surprising to me though. Z64. But still a little slower than one would like. But it could be, like, we could cut the time in half by doing this filtering up front, even. Could be significant. So let's do that. So let's say, let's take this out of here and turn it into a lambda. So let's say let constraint be this, and then don't do this, iter. This can be get surface such that, and we'll say at constraint. And then get surface. Whoa. We will call get surface such that, and it will have a constraint which will be a reference to a function from vec2 to bool. And we will have get points between. Is there any reason to filter during get points between rather than here? Sure there is. It's probably okay. Can I just say this? Dot filter. What's the issue here? Trait bounds. Mod 1 doesn't size. Ugh. It's not what I care about. So what if I say constraint B? Vec2 isn't an iterator. Oh, I'm just putting this in the wrong place. Okay. And if I do this, so V constraints V. Okay. And what's going on here? Dereference to borrow. Okay. Any reason not to just iter? I don't know. Let's see. Okay. That should get me my surface. And now what's going on here? Position. Oh, because now I'm using an iter, not an into iter. Sure. That's fine. And those are fine. Okay. See if we do any better with this. Whoops. Constraint type needs to be known at this point. What if I just say here that this is a vec2? Okay, so now at least we're not doing the filtering every time. We really weren't doing the filtering every time before, though. What else to say here? So the search space is pretty small. I mean, it's not that small, but it's small enough. We're using the best beacons. We're checking the best sensors possible first. Still failed. Oh, yeah, okay. It failed, but we get an answer. It's a little over a minute. I mean, on release mode, this would be faster, for sure. Pretty sure I'm not on release mode. But I don't know. Feels like there's still something here that could be even better. So, one thing that we could do is union all of the surfaces together. Like we get a bunch of hash sets. They're going to have some overlap. Probably not that much, though. Like, it's kind of going to be... It's a bunch of one-dimensional shapes, so they're going to intersect in, like, zero-dimensional ways. So it should just be a few points, which doesn't seem... that compelling. Beacon position. We could also flip the order we're going through these, so rather than going through all of the points, we could go through each sensor. Nah, that's not going to work, because then we're not going to know the answer until we go through the last sensor, and we really want to exit quickly. Well, it feels like there's a way to improve it, but I think I'm not going to if this is right. Oh, sorry if I'm dropping frames. Getting some warnings here. Hopefully that clears up. Okay, let's submit. Where is my... see how we do. Boom. Okay, we get it. So maybe not quite as good as it could have been, as optimized as it could have been, but still pretty happy about that. Let's jump into day 16. Proboscidea volcanium. Some sort of sticking out volcano in Latin, I guess. The sensors have led you to the origin of the distress signal, yet another handheld device just like the one the elves gave you. However, you don't see any elves around. Instead, the device is surrounded by elephants. You must have gotten lost in these tunnels, and one of the elephants apparently figures out how to turn on the distress signal. The ground rumbles again, much stronger this time. What kind of cave is this exactly? You scan the cave with your handheld device. It reports mostly igneous rock, some ash, pockets of pressurized gas, magma. This isn't just a cave, it's a volcano. You need to get the elephants out of here, quickly. Your device estimates that you have 30 minutes before the volcano erupts, so you don't have time to go back out the way you came in. You scan the cave for other options, discover a network of pipes and pressure release valves. You aren't sure how such a system got into a volcano, but you don't have time to complain. Your device produces report your puzzle input of each valve's flow rate if it were opened. Okay. In pressure per minute. Okay. It's pressure flow. Interesting. Okay. And the tunnels you could use to move between the valves. There's even a valve in the room you and the elephants are currently standing in, labeled AA. You estimate it will take 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. What's the most pressure you could release? For example, suppose you had the following scan output. All valves begin closed. You start a valve AA, but it must be damaged or jammed or something. Its flow rate is 0, so there's no point in opening it. However, you could spend 1 minute moving to valve B. 1 minute to go between them. Okay. And this is flow per second or something. You have 30 minutes total. 1 minute to go between them. So you have 30 things you can open, basically. 1 minute moving. Takes 1 minute to follow any tunnel from one valve to another. Okay. In doing so, it would release pressure during the remaining 28 minutes at a flow rate of 13. A total eventual pressure release of the product of those. Then you could spend your third minute moving to CC, so on and so forth. Making your way through the tunnels like this, you could open many or all the valves by the time 30 minutes have elapsed. However, you need to release as much pressure as possible, so you'll need to be methodical. Instead, consider this approach. You go to valve D. Yeah, sure. Each one takes a minute. Sure. This approach lets you release the most pressure possible in 30 minutes with this valve layout. 1651. Work out the steps you can release. You can work out the steps to release the most pressure in 30 minutes. What is the most pressure you can release? Okay. Let's do it. Let's do it. Input 16.txt. Okay. And do we have example input also? Yes, and we'll put it in a file. Example input 16, and it's this. Okay. So, problem 16. And let's just set up none of this. Let's write none of this, and then let's write a quick function to pull this in. Function get example input. Input parser new parse as string example input.txt. So our example test, or integration test, will be assert equals get example input. We want to solve problem 16a with the example input. We want to compare it to the answer, which is 1651. Okay. So this is an optimization problem. It's an optimization problem in which we need to work out, so all the valves start closed. How many total valves are we given in the full input? I assume more than 30. Yeah, 55. Okay, So we have to choose which 30 of the valves to open. Yeah. Minute 30. Minute 1. Okay, so I get to open exactly 30 valves. So I get to open exactly 30 valves, and I'm not trying to maximize the number of the amount of pressure, like the total rate of pressure. I'm trying to maximize the integral of that, like the cumulative pressure released over the remaining seconds. Is what I'm trying to do. Oh, hang on a moment. No, it's worse than that. You estimate it will take you 1 minute to open a valve and 1 minute to follow any tunnel from one valve to another. But I have to move between them. Okay. So it's a row of valves connected by a tunnel. Okay. Well, that's good and bad. That means that there are probably fewer possible solutions. So the picture that's forming in my head, crap. Sorry about that. Lost my VS Code. So we have A, B, B, C, C, all the way up to D, D or something. Okay, all the way up to some other complicated thing. Doesn't really matter. Let's say we have this. Starting at AA, all the valves are closed. So the quantity we're trying to optimize is like sum of like if a valve is open at time t, valve gets opened at time t, it has 30 minus t minus 1 or something, plus 1 or something time during which it releases some amount of valve of pressure per unit time. We're going to spend a minute to get there. So paths that we could take are things like open AA, walk BB, AA to BB, walk right, open BB, walk right, open CC, etc. We also have open AA, walk right, open B, open CC. So it's really just open, walk. Our options are open, walk right, and walk left, unless there is no left or no right, or it's already open. So that gives us a big tree. And we also have some relation. there's some like triangle relation here where once we've computed, let's see here, I think what this is going to end up coming down to is we should not have to recompute. There should be a bunch of things that we don't have to recompute for the different trees. So like certainly, so if we think about just AA, BB, CC, then we have open, we have OR, ORO, ORR, OR, no, LO, but substrings of these, you know, are O, LO, RR, O. Substrings of these are going to result in very similar outcomes that we shouldn't really have to recompute. I think is going to end up being the point. Because it matters, you know, say we have ORRO here versus here. Let's say we do nothing for these because we've already opened everything, which won't ever happen. But the only difference between this and, this ORRO and this ORRO is that there are 3 steps here where all 3 of them are open. But that's really easy to compute. So I think the idea here, like the naive way to do it is to just list out, like compute every possible path, walk the tree, and as soon as your path takes longer, I'm trying to find the most. Yeah, so you just walk every path and compute it. And then you can start to say things like, well, there's no way if I'm in the same spot, you know, if I'm at B and at the same time B at step 10, and I've already done a B at step 10 and it was better, then I can stop because there's no way that I can, like, I know how to improve on this. That's one thing we can do. The other thing we can do is compute how the different strings starting at different locations affect things, and then combine those in an intelligent way. I think that's going to end up being the key here. And I think we want to start at the end. So I think we want to say at time 30 or 29, when does it end? At minute 30, at t equals 30. At A, yeah, but it depends on what's open and what's closed. So at time equals 30 at position A with A open, B open, we should open A. That doesn't do anything though. So at t equals 30, it doesn't matter what we do. No pressure will be released. At t equals 29, at A with A closed, B closed. Actually, with A closed, it doesn't matter what we do. At t equals 29, at A with A open. Wait, with A open, it doesn't matter what we do. Because it's already open. With A closed, we should open it. At B, same story. At C, same story. At t equals 28. At A with A open, B open. Doesn't matter what we do. B open, or with A closed, B open, we should open A. With B closed, A open, we should go right. And so on. And in general, we're going to have situations like at B with A ... and it's going to take, there are going to be however many cases there. But we can compute the optimum in each of these situations. And note that the answer to the 28 question is going to depend on the 29 question, and the 27 question is going to depend on the 28 question, and so on. And by doing that, we're really avoiding a lot of double computation. I'm not sure if this is going to be efficient enough, but I think it's definitely the right starting point, and then we can optimize from there. So let's do that. So we're going to have to parse problem 16. We're going to have to do some parsing. The parsing's not really that hard, though. Let's see here. What tests do we want? Test parsing. So this is going to be something like let valves be valve from strings, get example input, assert that the example input is however 10. And what to say, like, I guess we'll just assert that valves 0 dot get pressure I don't actually care what they're called, right? Oh, shoot. Okay, the tunnels are not sequential. I don't think that really changes anything. I think the analysis still works, but we do care what the names of things are then. It's not just left and right. It's that they can go to any of their neighbors. I guess it does change some things. It means that we're much less likely to have substrings repeat. But I think it's still okay. Also, F, G, and I should never be opened here. There might be similar cases. Kind of interesting. So and I guess the other thing is that in theory we can end at any valve. So we have to check every ending point. But okay. I mean, I still think this is the right approach. So let's get pressure, and we just need to check. So maybe let's just copy this over for test writing purposes. So pressure is 0. Let's check. J is 10. So 9. 1. Okay. And then how will we want the valves to know about each other? So we can just have them carry around a numerical index. And maybe we also give them names. So we say assert equal valve 0.label is aa.string and assert equal valves 9 label is jj.toString. And then the way they'll know about each other is just by having indices to each other. and then the algorithm will be start at time equals 29 at each of the run through each of the potential locations, get back the best result for the best option for each, go to time 28, do the same thing, and so on. And for that, we'll just keep around do we want to keep around a hash map, or do we want to, I mean, the valves shouldn't know anything about that. The valves should just know what their neighbors are. So let's say assert equal valves 0 dot get neighbors is let me go back to fine. DD DD is 3, II is 9 is 8, and BB is 1. And 9 is just 8. And we should also say let's say assert that valves iter all v dot is closed, yes. And then we can say let valve is let mute valve is valves dot valve 0 valve dot open, assert that valve is open, assert not valve is closed. Okay. And we also want to be able to say how much pressure each valve will release at some specific time. So assert equal valve get cumulative pressure from, and the from will be the time when it's opened. And so that will be, so let's do from, if it's opened at 30, it should be 0. If it's opened at 29, it should be, oh, it's still gonna be 0. Let's see. Let's say valves 9, which has flow rate 21. And we'll say at 29 it should be 21. At 28 it should be 42. And at 0, or at 1, sorry, at 1, it should be, if it's opened at 1, that means that at every subsequent minute it's going to go, and there are 29 of those. 29 times 21. And let's just, we'll give this a really long name, but, okay, it's fine. Okay. And I gotta wrap up in the next 15 minutes or so. And so the algorithm itself should be run. Let's actually just implement the parsing, because I think I can probably do that in 15 minutes, and then we can start with the algorithm itself next time around. So, struct valve. Let's derive some stuff. We can derive virtually everything, I think. I don't want default. Do I want hash? I might want hash. I'm not going to be able to have this be copy, though. It's going to have a vector in it. So it is going to have a label, which will be a string. It's going to have a flow rate, which is going to be a U32. It's going to have a neighbors, which is going to be a vec of usize. We will impl valve. We will have a new function. Label string, flow rate, U32, neighbors, vec usize. It will return a self. It will return self of label flow rate neighbors. We will have a function called getLabel. It will return a string. It will be self.label. We will have a flow rate or pressure. What do they call it in the input? Flow rate. Pressure per. Pressure per minute. Pressure rate. Something bothers me about that units wise, but I'm not going to get into it. Flow rate is fine. U32 self.flow rate, and this should be a reference. Self.neighbors. Okay. And I have to clone this, I guess. Okay. What else to say here? We need from strings. That will take a vec of string. It will return a vec of self. And for this, we'll say, do we want a parser? We don't really need one, right? we can just split. We'll just split the pieces. So, let halves be string.split on collect into a back. We will say assert halves dot length is equal to 2. Oh, this is strings. So then this is going to be pub function from string. And this is just going to be strings.into_iter.map. Can I just say self from string? And then string we split in half, we check that there are 2 of them, we say let flow rate half neighbor half be halves 0 halves 1, and and now valve, okay. I guess we split on equals. Let flow rate, label, and flow rate be s.split on equals. Again, we check that label and flow rate dot length is 2. And then let flow rate be label and flow rate 1 dot parse into a u32. And we can wrap that. And then we want the label, which will be the second component out of 5 if we split on white space. So let's say let label parts be label and for flow rate 0 dot split on white space. Check that there are 5 parts. Just a poor man's parser. And now we let label equal label parts 1. And then at the end here we need This is a little annoying. Tunnels lead to valves. We just want to skip. So let's say let neighbors string be neighbor half starting at this. Dot length. And then let neighbors equal neighbors string dot splits on this guy dot map s dot parse into a. Oh no, I don't have to parse it. I just split it and collect it. Collect this into a vec. And then we return self new label flow rate neighbors. And these all have to be strings. And I can't spell. Oh, this is not a string. And neighbors is also not a string. Will this cast? It will not. Oh, neighbors should be. Oh, interesting. I forgot. I wasn't doing this by the labels. I'm doing this by. It should be pointers. Okay, that's a little bit trickier. I wonder if we return a hash map with the pointers. A hash map with the labels. Might make debugging easier. I think let's do that actually. And then I gotta go in a minute. Hash map. I guess it's just a vec of string. I don't like that. I don't like that. All right. I'm gonna call it here just because I'm out of time and this is getting a little bit, it's gonna be a little bit finicky, mapping, just getting the indexes. So I will start there next time, and we will implement, and then we'll jump into implementing the algorithm. But hope everybody is having an excellent Thursday. Please like and subscribe on YouTube. Please follow me on Twitch. It's super helpful. And I'll catch you guys soon. Have a good one.